All right. Okay. Um, Good afternoon. Um, my name is Charles Nye, and I'm with BASF Corporation in Cleveland, Ohio. And I'm honored to be today's speaker for the ASCC webinar, which is titled Benefits of Chemical Admixtures in Concrete Construction from the Contractor's Perspective. The objective of this particular webinar is to provide a concise overview of the benefits that chemical admixtures can provide to contractors. And what I intend to cover today will be just touch on what these chemical admixtures are, what their benefits are in concrete construction, and along the way I'll also address some potential issues that can crop up and how we troubleshoot those particular problems. So let's start off. And the big question is, okay, what is an admixture? Now, believe it or not, there is a definition, an official definition for what an admixture is. And essentially, it is any ingredient that is added to a concrete mixture other than Portland cement, water, aggregates, and fibers. Now, obviously, when we look at the things that go into chemical admixtures, into concrete then, other than these materials, they can be broken down into two different classifications. What we call chemical admixtures, which are typically either in liquid form or powder form. And these materials are typically added in very small quantities relative to the other materials that we have in making concrete, such as the Portland cement or the aggregates. Now, in addition, previously, we used to have the term mineral admixtures, which basically referred to what we now call supplementary cementitious materials, or SCMs. And these are materials such as fly ash, either Class F or Class C, as well as slag cement, metakaolin, or silica fume. Now, these materials will not be covered in this particular seminar, and the primary focus will be on chemical admixtures. Now, the big question is, why do we need chemical admixtures in concrete? Well, it turns out we use them to enhance the properties of concrete and, in some cases, mortar in either the plastic or the hardened states. And the benefits that they provide include these that I've listed, for fresh concrete. One of the primary reasons why chemical admixtures are used in concrete is to decrease the total water content of the concrete mixture. And there are significant benefits that come about from doing so, which I'll cover in the next slide. Another reason for using chemical admixtures is to increase the workability of concrete, to make it easier to place, consolidate, as well as finish the concrete. We also use chemical admixtures to either retard or accelerate the time of setting of the concrete, depending on the time on the particular season. We also can entrain air in concrete using chemical admixtures. Other benefits include reducing segregation, reducing the rate of slump loss, also improving things such as pumpability, placeability, as well as finishability of concrete. And then finally, we can also use chemical admixtures to either modify the rate of bleeding or the amount of bleeding that actually occurs in concrete. Now, in the hardened state, the benefits of chemical admixtures can be summarized under these three bullets. Primarily, we can use them to increase strength, to increase durability, or to improve aesthetics. Now, these are the main classes of chemical admixtures that exist. And I've divided these under water-reducing admixtures, which form the largest grouping of admixtures that are used, and followed by set control admixtures. And then we have a broad class of admixtures that fall under what we call durability enhancing. So these are materials that are used to actually help the concrete withstand the environmental conditions during service. And then finally, there are some miscellaneous chemical admixtures, such as viscosity modifiers and rheology control materials, coloring admixtures, and so on, that also exist. All of these admixtures typically are governed by industry standards, and specifically the ASTM standards as well as the AASHTO standards for those who may be involved in paving applications. The two main standards that exist for chemical admixtures are ASTM C260, the AASHTO equivalent is AASHTO M154, and this particular standard covers air and training admixtures. Now, the bulk of admixtures fall under ASTM C494. The AASHTO equivalent is AASHTO M194, and this is the main Bible basically for chemical admixtures. Now, within ASTM C494, there are different types that are listed, and up until fairly recently, there were just 7 types, going from A through G. Type A's, as most people call them, are the water-reducing admixtures. And then we have Type B, which is retarding, Type C, accelerating, Type D will be water-reducing and retarding, Type E's are water-reducing and accelerating, so these have accelerating components to them. F will be water-reducing, high-range, and then Type G's are the water-reducing high-range with retarding components. Now, several years ago, a new type was added, and this is Type S for specific performance admixtures. And this is supposed to cover admixtures that neither provide water reduction nor affect the setting characteristics of concrete. And under this classification, admixtures such as rheology control or viscosity modifying admixtures, shrinkage reducing, basically will fall under this particular Type S category. So I'd like to ask the question from the contractor, since we're trying to do this presentation from the contractor's perspective. And I put down a few bullet items. Now, most contractors, I believe, would want to have concrete that arrives consistently at the job site, having the desired slump and air content where applicable. In addition, the paper concrete should be able to maintain the slump and workability throughout the placement if possible. It's got to be able to pump well and respond well to consolidation efforts as well as vibration. As well as in flat work applications, it has to finish well. In addition, most contractors I know definitely would want the concrete to set at the time that they would like, irrespective of the ambient conditions, and preferably the same time of setting all year round if they happen to be working on the project that extends over the seasons. It's got to also be able to develop strength as needed, both early age as well as long term. It has to be also durable. And finally, most contractors I know would want to have concrete that will make challenging concrete applications fairly easy. Now, when it comes to concreting and proportioning and producing concrete, there is always a balance that has to be drawn between workability and strength. Because on one hand, the contractor needs workability, both initial as well as over the placement period, in order to get the concrete into place without too much problem. And one of the things that helps with workability is actually adding more water. So before the advent of chemical admixtures, one way of increasing workability was to add more water or to add more cement to the mix, and by so doing, also increase the water content accordingly. On the other hand, from a strength perspective, the concrete producer is interested in using less water because reducing the water content increases the compressive strength, both early age and long term. So it would appear as if we have a conflict where on one hand, the contractor would like to have more water in the mix to improve the workability, and on the other hand, the concrete producer would like to have less water in order to improve the strength of the concrete. And at this point, what I'd like to bring up this caution, and that is that the indiscriminate use of water at the job site to improve slump and workability will invariably reduce the strength and durability of the concrete, as well as increasing the drying shrinkage of the concrete. So as much as possible, the best thing is to keep the water content as needed and have ways in which we can improve the slump or workability of the concrete. And this can be done fairly easily through the use of water-reducing admixtures. By using admixtures, we can safely improve slump and or workability without adversely affecting the strength and durability of the concrete that's in place. So let's start off and take a look at what these materials are. Well, as the name implies, water-reducing admixtures are used for the sole purpose of reducing the quantity of mixing water required to produce concrete of a given consistency. That's one of the primary reasons why these admixtures are used in concrete. And there are different types of water-reducing admixtures. We have the normal types, which will fall under the ASTM C494 Type A category. And then we also have mid-range water-reducing admixtures and high ranges that fall under the ASTM C494 Type F category. Now, in between, we also have the mid-range water-reducing admixtures, which at this point in time are not necessarily covered, are not covered by any one particular ASTM C494 category, but most of them do meet the Type A category. Now, with these admixtures, we can produce concrete over a wide range of slumps, from low slumps to moderate slumps to high slumps, as well as self-consolidating concrete. Now, the main benefits of water-reducing admixtures can be summed up under these three bullets, part of the reasons why they're used. As I indicated earlier, the main purpose is to improve slump and workability of the concrete, and this can be achieved without necessarily reducing the water content of the concrete. They can also be used to increase strength and reduce the drying shrinkage of concrete by reducing the total mixed water content while maintaining the slump and workability of the concrete. And finally, they can also be used to economize the mix by lowering the cement and water contents without necessarily affecting the strength and workability of the concrete. Now, when we start off with the Type A or the normal water-reducing admixtures, these, by specification, have to provide a minimum of 5% water reduction when used in concrete. And they're used primarily in concrete that would typically have slumps of no more than about 5 inches. They can also be used synergistically with other types of admixtures within the concrete portfolio. Now, the typical dosage ranges of these admixtures will be anywhere from about 2 to 5 fluid ounces. And in some instances, as we go to the higher dosage levels, 5 ounces, 4-5 ounces and beyond, we find that you have diminishing returns with respect to additional water reduction. However, as you increase the dosage, you also increase the potential for retardation as well as bleeding. And with the water-reducing admixtures that may be based on lignins or lignosulfonate salts, as if more known, you may also run the risk of increasing the air content of the concrete. Now, obviously, all of these can have an impact on early age strength development. And this was one of the reasons why the mid-range water-reducing admixtures were developed. Now, the mid-range water-reducing admixtures, even though there's no specification, typically provide water reduction between that which we get with normal water reducers and what we get with high-range water reducers. So, in effect, they provide water reduction between 5 and 12%. And they work extremely well in the mid-range slump of about 5 to 8 inches. The dosages of these materials can range anywhere from about 3 to 15 fluid ounces per hundredweight, depending on the chemistry of the material. And they are designed to have controlled setting characteristics even at the higher dosage levels. And they can be based on lignosulfonate salts, lignins. Some of the newer technologies are based on the newer admixture chemistry, dispersant chemistries, which are the polycarboxylate ether technologies. In addition, most of these mid-range water-reducing admixtures also contain what we call set balances, as well as strength and finishability enhancing ingredients. And they can also be used in combination with high-range water-reducing admixtures to provide synergistic performance. Now, the benefits of these mid-range water-reducing admixtures basically lie in their excellent finishability that they provide, especially in lean and harsh mixes, working with supplementary cementitious materials. Mixes that tend to be sticky can benefit from the use of most mid-range water-reducing admixtures. Typical applications for these materials include flat work, curb and gutter, and so on. One of the other benefits of mid-range water-reducing admixtures is the fact that they provide superior pumping characteristics when used in concrete, which results in reduced pump line pressures and also the ability to pump over longer distances because of the effect that they have in reducing pump line pressures. However, there are some potential issues with these materials as well, and this includes some of these issues are typically product dependent, and that includes retardation at higher dosages, as well as undesirable air contents when they're used at relatively high dosages. So these are just some issues that are typically looked out for with the use of mid-range water-reducing admixtures. But for the most part, they're used very widely within the industry in applications that range from flat work, formed surfaces and precast, pumping, low slump machine placements, as well as in areas where increased use of pozzolans occur. And this is again because of the impact that they have in reducing stickiness of concrete in the mixes. Now, the last category under water-reducing admixtures will be the high-range water-reducing admixtures, or as they're more commonly known within the industry, superplasticizers. And these admixtures, by specification, have to provide a minimum water reduction of 12% when used in a concrete mixture. Most of them actually provide water reductions much greater than that, and in the extreme cases, we can get as much as 40% reduction in total mixed water content. The main benefit of high-range water-reducing admixtures is that they're used in producing flowing concrete. So these are concretes that have slumps of 7.5 inches or greater. The ideal slump range for most of these materials will be 8 inches or greater. And they can be added either at the batch plant or at the job site. Initially, when these materials were developed, based on the first generation, second generation type technologies, they were based on lignosulfonate salts. which had very short pot life. And as a result of that, job site addition was a preferred method of using these materials, because once they were added to the concrete and mixed into the concrete, then the concrete could be placed right away. However, with the newer technologies that are in place, much better control can be achieved with the addition of these materials at the batch plant. Now, with the new chemistries that are based on polycarboxylate ether, the dosages of these materials that are used in concrete currently will be less than about 10 fluid ounces per hundredweight, compared to the older technologies based on naphthalenes and melamines that would typically be used at dosages greater than 10 fluid ounces per hundredweight. The main benefits of high-range water-reducing admixtures lie in the fact that they do provide significant water reductions, as we saw on the previous slide, anywhere from about 12 to 40%. And as a result of that, they are the main admixture of choice in producing high airly as well as concrete that have high ultimate compressive strength. They are also the admixtures of choice when we're looking at producing concrete with low permeability or increasing the durability of concrete. And they also provide more effective use of cementitious materials in concrete. In addition to that, the other benefit of high-range water-reducing admixtures is the fact that they can be used to provide high slump and workability, which can result in faster discharge, pumping, and placement of concrete, as well as reducing the effort required to vibrate concrete in place. However, just like any of the other admixtures I talked about so far, there are some potential issues which could be segregation if the dosage that's used is not in balance with the total water content of the mix. In addition, especially with the older technologies, high-range water-reducing admixtures can potentially also lead to some amount of retardation. This is not that much of an issue too much these days with the newer polycarboxylate ether technologies. Also, high-range water-reducing admixtures, when used at lower slumps, can lead to erratic performance. Years ago, there were some state agencies that will permit the use of high-range water reducers, but then limit the slump to no more than 5 inches. And that created a lot of havoc or problems, with respect to the slumps and the performance. These days, I think most agencies understand that these materials have to be used at much higher dosage, much higher slump levels, and are open, to that. Now, obviously, having high slump does not necessarily mean that we may be able to achieve, extremely good consolidation in the forms, depending on how congested the reinforcement is. And one of the things this has led to that has been facilitated by high-range water-reducing admixtures is self-consolidating concrete. Now, self-consolidating concrete, by definition, is a highly flowable, non-segregating concrete mix that can flow into place, fill the formwork, and essentially encapsulate the reinforcement without any mechanical consolidation, or, if required, very, very little mechanical consolidation. Now, in this particular photograph, this was a project that was done in South Carolina, the Citadel, and it shows on the right-hand side of the picture 7-inch slump concrete vibrated in place at the non-SEC versus self-consolidating concrete that was applied without any vibration whatsoever. And I think the picture basically tells the story. With self-consolidating concrete, the surface finish can be significantly enhanced, and sharper edges can result, even though the concrete may not be vibrated. And on this particular project, where there was we had a lot of architectural details, the use of self-consolidating concrete, resulted in extremely good finish in the final structure. Self-consolidating concrete has also been used and is being used quite extensively in mat foundations. It was used on the Burj Khalifa in Dubai, and in the U.S., Skidmore, Owens & Merrill also specified it for use in the Trump International Tower and Hotel project in Chicago back in 2005, where a total of 4,600 cubic yards of self-consolidating concrete was placed in a total of 22 hours continuously. The mat was 198 foot long by 60 foot wide and 10 feet deep. Another area where self-consolidating concrete is being adopted, especially by a lot of state agencies, is in drill shaft construction. And this is because with the change in detailing to accommodate seismic activities and so on, the hoops are now much tighter. So even with the use of just normal superplasticized concrete, the typical H9-inch slum concretes, the concrete may not necessarily flow out of the cage, resulting in the photographs that we see on the screen now. With self-consolidating concrete, it's been shown that the concrete can rise uniformly, within the shaft, because of the high fluidity of the mix, resulting in very, very few defects. And one of the projects where it was used extensively was in the I-35 West Replacement Bridge in Minneapolis, Minnesota, a few years ago, where all of the drill shafts on this particular project, were basically cast using self-consolidating, concrete. So let's switch gears now and talk about the air, the specified air content. Why do we need air in concrete? Well, these pictures tell the story. The effects of cyclic freezing and thawing, can be devastating on concrete that is not proportioned for those cycles. And as a result of that, it can also lead to scaling, as we see in here. Now, as a result of that, air entraining admixtures or entrainers are typically used in concrete, and the primary purpose is to basically stabilize tiny bubbles in the concrete that are formed in the concrete during the mixing process, and by so doing, provide protection to the concrete against cyclic freezing and thawing under saturated conditions. Now, it turns out entraining admixtures also help improve the workability of concrete because of the ball-bearing effect that they provide. Now, the air, as I indicated, is basically generated into the concrete during the mixing process when the air entraining admixtures are used. And they form air bubbles that are spherical in nature, as opposed to the irregularly shaped, larger entrapped air voids that really do not provide any benefit when it comes to cyclic freezing and thawing. And in hardened concrete, the air bubbles, this is what the air bubbles look like. The circles that you see that look like lunar objects are basically the air bubbles. And they come in different sizes and shapes, and predominantly the ones that provide benefit in concrete are the smaller sized bubbles that basically provide relief to water that may be freezing in the concrete during a freezing episode. Now, there are different types of entraining admixtures in the marketplace, and entrainers, as I indicated at the beginning, are governed by ASTM C260. But the entrainers in the marketplace can basically be classified under the wood-derived products as well as the synthetic materials. Now, both of these have their benefits and slight disadvantages. With the Vinsol resins or the wood-derived products, you get quick air generation, but minor air gain with continued mixing. However, over time, air loss can result with prolonged mixing. Now, these vent hole resins and rosins, tend to form mid-sized air bubbles, and most of them are basically formulated and are compatible with most chemical admixtures that are used in concrete. Now, the synthetic materials also generate air quickly, but then they're not as effective in very low slump mixes, such as those that may be used in paving applications. These materials, again, also the synthetic materials, will have minor air loss with mixing. They generally form much smaller, very stable air bubbles, when used in concrete. And they may be somewhat incompatible with some high-range water-reducing admixtures, depending on the particular chemistry. But both of these chemistries, either the vent hole resins or the synthetic materials, are very, very effective in producing concrete that has very good freeze-thaw resistance. Now, one of the things that I would like to point out talking about these materials is that in a study that was done by the Portland Cement Association years ago, one of the things that they found out was retempering, the indiscriminate use of water at the job site can affect the air content of the concrete, and depending on the chemistry of air content used, actually lead to clustering of air voids around the aggregates. So that is one reason why it's not necessarily a good idea to always retemper concrete at the job site. Now, the benefits of air entraining admixtures in plastic concrete include improving workability, increasing slump, reducing segregation and bleeding, producing a more cohesive mix, and then also, in some cases, reducing the density of concrete. In having concrete, the main benefit is improving resistance to freeze-thaw distress, as well as scaling due to de-icing salts. Now, they also produce a slight decrease in permeability, which can result in improving water tightness as well as sulfate resistance. But for the most part, if we're interested in reducing permeability, there are more effective ways of doing so with high-range water-reducing admixtures and supplementary cementitious materials than using air entrainers within the industry. Now, the disadvantages of air entraining admixtures in concrete basically include the fact that sometimes the mixes can be sticky, and in addition, because of the air bubbles, they tend to reduce the amount and rate of bleeding. Now, in addition, entrainment can reduce the strength of the concrete, approximately 3 to 5% for every percent increase over and above what the concrete was designed for. And entrainers may also lower the abrasion resistance depending on the effect that they have on compressive strength. With respect to things that affect entrainment, anyone who's ever worked with entrained concrete will know that they're extremely touchy, and pretty much everything that you can think of can affect the entrainment in concrete. And these include things from the batch plant, such as the aggregate gradation, the cement changes, the use of supplementary cementitious materials, especially class F fly ash, depending on the carbon content and so on. And at the job site, things such as the addition of water, high-range water-reducing admixture, pigments, fibers, and so on, also affect entrainment. Pumping is also one thing that can affect entrainment, especially if we have a vertical drop at the end of the pump line. Now, temperature affects the hydration of Portland cement, which basically means that in the summertime, the concrete tends to react much faster, and in the wintertime, it tends to react a little slower. Now, as a result of that, in the summertime, some of the issues that potentially can arise include increased water demand and rate of slump loss for the concrete, an increase in the potential for retempering of the concrete at the job site, a higher potential for plastic shrinkage cracking in the concrete, and if there are delays, the potential for cold joints. In addition, because of the higher temperatures, the concrete tends to set faster, which can lead to problems with placing, consolidating, and finishing, the concrete. With respect to cold weather, the exact tends to happen. The concrete sets slower, and this can increase the potential for plastic shrinkage cracking if the surface of the concrete and flatwork is not protected. In addition, strength development, especially early age strength development, will tend to be impacted as well. Now, as a result of that, we use admixtures, to control the time of setting of the concrete. Now, these admixtures are basically called set control admixtures, and they're used to modify the setting and strength development characteristics of the concrete. Now, these fall under two different groupings: retarders and accelerating admixtures. Now, retarders are basically used to offset the acceleration that can occur under hot weather conditions. And some of the benefits include also long hauls, depending on the type that is used. Now, when I talk about long hauls, I'm not necessarily referring to distance. It could be that even in an urban environment, due to traffic congestion, it takes a longer time for the concrete to be transported from the batch plant to the job site. But the benefits of these retarding admixtures include minimizing the potential for cold joints, providing sufficient time for finishing operations in hot weather. In bridge deck application, they permit full form deflection before initial set of the concrete. And as I indicated, they also facilitate long hauls, such as this particular example that I'm showing, where concrete was hauled a total distance of 250 miles over a time of 8 hours. And upon arrival at the job site, the concrete still had a very decent slump of 4 inches and could be placed without too much problem and without having to add additional water to the mix. In this particular case, a hydration controlling admixture was used at a dosage of 8 fluid ounces per hundredweight of cement. So my question to you is, why is it that engineers stick hard and fast to the 90-minute 300 revolution limitation when obviously within the industry there are technologies that can be used to permit placement of concrete way beyond these particular limits? Now, with respect to potential issues with retardation, with retarders, the potential for over-retardation exists, if there's an overdose of admixture or depending on the other constituent materials that go into the mix. In addition, extended exposure time may increase the susceptibility of flat work to plastic shrinkage. But one of the more common problems sometimes that occurs is rapid stiffening when a retarder is used, and slump loss associated with that, depending on the cement chemistry and the type of material that is being used. So even though retarders are supposed to extend the time of setting, sometimes with some cements, you could have the exact opposite happening, where you end up with rapid stiffening. Now, accelerating admixtures, on the other hand, are used to do the exact opposite. And when the weather cools down, accelerators are added to concrete to shorten the time of set and also to accelerate early age strength development. The main types are the chloride-based admixtures, which are very effective and are typically used in residential applications, non-reinforced applications. But for reinforced concrete applications, the non-chlorides exist. And within the non-chlorides, there's a subcategory that are used in sub-freezing ambient temperature environments. The main benefits are to reduce the time of set of concrete, to increase early age strength development, which will then permit earlier stripping and reuse of forms. These can also help reduce protection or the heating requirements that may be needed in cold weather application. And overall, they facilitate the earlier use of a structure or a pavement. Now, consistency was one of the things that I indicated will be the desirable thing with respect to a perfect concrete for a contractor. But one of the things that we know, especially when we are just slumped at the job site, is that then we're playing with the consistency of the mix. Now, there is now in the marketplace a workability retaining admixture that was developed back in 2009. So we're talking about 4 years ago. It was introduced about 4 years ago, which basically provides varying degrees of workability retention depending on the dosage used. And the main benefit of the workability retaining admixture is that unlike a retarding admixture, it does not retard the time of set of the concrete, and as a result of that, it does not impact early age strength development. It's primarily used in moderate to high slump concretes, including self-consolidating concrete, but it's also been used in lower slump concrete mixes. And here's just some performance data that I'd like to share with you. This was a project where the specified compressive strength was 5,000 psi, but more importantly, the target slump was 6 to 8 inches, and the target air content was 5 plus or minus 1.5%. And the average of 107 records was an average slump of 7.4 inches and an air content of 4.7%. Needless to say, the contractor on this project was extremely pleased, with the performance of the concrete, as was the concrete producer. So just to summarize, the benefits of the workability retaining admixture basically lie in the fact that it helps to minimize slump adjustments or retemping at the job site, and as a result of that, promotes greater consistency of concrete workability, air content, and compressive strength, which invariably enhances the in-place performance of the concrete mix and leads to fewer rejected loads as well as faster track turnaround time. Now, let's switch gears now and talk about durability enhancing admixtures, because we've already covered water reducers, entrainers, as well as set control admixtures. But what we see in specifications now more and more are also durability enhancing admixtures. And these materials are added to concrete primarily to improve concrete durability. Now, they include entraining admixtures that I've already covered, as well as lithium admixtures for mitigation of alkali-silica reaction, corrosion inhibitors, shrinkage reducers, and waterproofing admixtures. So these are the common durability enhancing admixtures that are currently being used in the industry. Let's start off with the admixtures for mitigation of alkali-silica reaction. Now, alkali-silica reaction is a very destructive reaction that occurs in concrete due to a reaction between the alkalis in the cement and reactive silica that may be present in some of the aggregates that are used. There are various ways of mitigating alkali-silica reaction, but from an admixture perspective, lithium-based admixtures are very effective in doing so, as shown in this particular graph. However, one of the things to keep in mind is lithium-based admixtures are very expensive, but the good news is they do work synergistically with certain pozzolans, in particular Class F fly ash, slag cement, as well as metakaolin. And so they can be used in combination with these materials to provide economical solutions to alkali-silica reaction in concrete. I think I skipped a slide. The next group of durability enhancing admixtures will be the corrosion inhibiting admixtures or corrosion inhibitors, which are added to concrete primarily to mitigate chloride-induced corrosion of the reinforcement. Now, the main chemistries or the primary chemistries that are used in the marketplace are a 30% solution of calcium nitrite, as well as an organic solution of amines and fatty acid esters. Now, these materials work differently. The calcium nitrite, which is organic in nature, is typically used at dosages ranging from about 2 to 6 gallons per cubic yard. In most applications, such as parking garages, anywhere from about 3 to 4 gallons is typical. In marine applications, then you get into the higher dosages of around 5 gallons per cubic yard. The aqueous solution of amines and fatty acid esters is typically used at an optimized dosage of 1 gallon per cubic yard. Now, the main benefits of calcium nitrite is the fact that it can be used with admixed chlorides, and it also accelerates the time of set of concrete. So as a result of that, in the wintertime, it can double as an accelerator without having to add an additional accelerator to the mix. And for the most part, in my experience, calcium nitrite inhibitors typically provide compressor strengths that are either equal to or better than the mixes without calcium nitrite. I did mention that it does accelerate. Now, that can be a disadvantage as well, especially if you're concreting in the summertime when temperatures are high. And as a result of that, calcium nitrite inhibitors are typically used with a retarding admixture. And since the introduction of the Workability retaining admixture, we found that it also helps significantly in controlling the accelerating effect of calcium nitrite. The amine ester inhibitor is a normal set product, so it doesn't affect the time of set of the concrete, and it works by means of a twofold mechanism, which is one, reducing the permeability of the concrete, and also providing an increase in the chloride threshold at the surface of the steel. Now, because of the reduction in permeability that you get with this material, it also provides a modest increase in sulfate resistance when used in concrete. The main disadvantages of this particular product is the fact that it does require increased dosages of air entraining admixtures when used in concrete. And also, depending on the composition of the mix, some loss in compressive strength may occur, typically in the range of about 5 to 10%, depending on the mixture. But for the most part, when used in concrete mixes that are proportioned for corrosion resistance, the loss in strength is not anything that affects the specified compressive strength of the concrete. Another disadvantage of this material is the fact that it cannot be used with admixed chlorides in concrete. Now, shrinkage-reducing admixtures are another group of admixtures that are increasingly being used in the marketplace. And the main purpose is to reduce the drying shrinkage of concrete. And by reducing the drying shrinkage of concrete, reduce the potential for drying shrinkage cracking and curling in slabs. In water-retaining structures, they also help in providing or improving the water tightness of the structures. These materials are typically used at dosages ranging from about half a gallon to 1.5 gallons per cubic yard, depending on how much shrinkage reduction is actually needed in the concrete. A lot of times I get calls from specifiers who say that, okay, they want to use the maximum dosage, which I always advise against, because as you increase the dosage, not only do you increase the cost, but then you may also increase some of the potential impact on concrete properties, such as difficulties with entraining air and, in some instances, retardation. But these materials are very effective, and in the short term can reduce the drying shrinkage by anywhere from 50 to 80%, and in the long term, anywhere around 30 to 50%. They've also been found to provide benefit in the ring test. This is an ASTM procedure, that uses a restrained ring, and as shown in this particular graph, the shrinkage-reducing admixtures have been found to provide benefits in this situation. Now, what does that translate to in real life? These are pictures that I got from Caltrans, where currently these materials are being used in bridge deck applications. This was a control mix without the shrinkage reducing admixture, and after 9 months, they had through depth cracks in this particular bridge deck. The companion bridge deck without with the shrinkage reducing admixtures exhibited no cracking whatsoever. Now, these materials, as I indicated earlier, may affect the plastic properties of concrete, and these include potentially increasing the bleed time as well as the bleed ratio, and then also, depending on the ambient conditions, they could delay the time of set of the concrete, especially when used at the very, very high dosage levels. They can also have an impact on the air void structure, and as a result of that, most manufacturers or suppliers recommend the use of synthetic-based entraining admixtures when shrinkage-reducing admixtures are used. In hardened concrete, some loss in strength may be experienced depending on the dosage, but typically it's very minimal. Other issues, the cost of these materials. They're not, just like the lithium-based admixtures, these are fairly expensive relative to other admixtures that may be used in concrete. But the main benefits, again, include reducing drying shrinkage and the potential for subsequent cracking, reducing orthogonal shrinkage, curling, and then also providing water tightness and improving durability overall. Some of the other specialty admixtures that are used in the marketplace include viscosity modifiers that are increasingly being used in underwater concreting as well as self-consolidating concreting. There's a rheology controlling admixture that's used in relatively low slump concrete to improve extrusion of the concrete. And then we have other miscellaneous admixtures such as those that are used for flowable fill, liquid coloring admixtures, as well as water repellents. Now, one of the things that I talked about was the fact that admixtures can help make challenging concreting applications easy for contractors. And I'd just like to talk about a couple of challenging projects where admixtures really enable these to take place. The One World Trade Center building in New York City was recently completed. The antenna was added onto it. Now, this particular project, for those of you who may not be aware of it, consists of 4 high-rise buildings, the 9/11 Memorial, a transportation hub. And what is unique about the concrete that was used in this project was the fact that up to 74% of the Portland cement was replaced with supplementary cementitious materials, a combination of fly ash, slag cement, and silica fume. The concrete was designed for 4,000 psi, 14,000 psi in some of the applications, but they ranged anywhere from 4,000 psi to 14,000 psi. And all of it was basically self-consolidating concrete. And as we can see here in this particular mix design, the supplementary cementitious materials for the 3 mixes shown here ranged anywhere from 65% to 70%. But the system of admixtures that were used essentially allowed the concrete to be pumped all the way up 90 stories without any problems, and for the strength to be developed without too much issue. And as a result of that, the One World Trade Center actually won the Concrete Producer Reader's Choice Award in 2010 for the use of high-performance green concrete. This was as green as you could get the concrete to be. Admixtures are also being used in innovative high-performance concrete applications, such as what we call the strength on demand. These are concrete mixes that produce or that can yield very high strength shortly after placement, typically within 3 to 4 hours after placement. And as a result of that, they lend themselves very well for use in replacing deteriorated sections of concrete pavements, or also in other industrial facilities. But again, it's the system of admixtures and the use of these admixtures that allows these to take place. Now, I'd like to end by just touching on one thing, and that is addressing incompatibility between concrete materials, because a lot of times when issues arise at the job site, the basic or the typical tendency is to basically assume that there's something, wrong with the chemical admixture. Well, incompatibility occurs between concrete materials, which can lead to issues such as rapid stiffening, undesired air contents, excessive retardation. Sometimes it may result in higher admixture costs in order to address the issue, or other types of collateral effects such as cracking or low strength. Now, typically, this can be due to any one of the materials that go into making concrete. Either the cementitious materials, the chemical admixtures. Sometimes these can also be due to the aggregates or even the water that's used in making the concrete. And then, of course, Mother Nature can sometimes play havoc. So we occasionally may run into situations where the mix works well on this day, and then the next day something doesn't go right, and sometimes it happens to be due to the effects of the ambient conditions. So just to summarize, chemical admixtures can be used to enhance the pressure and hardening properties of concrete and mortar, and in concreting today, they form an essential component of concrete mixtures, in particular when we talk about high performance concrete. But for the most part, as shown in this particular slide, depending on the desired property, there is or there will be a combination of chemical admixtures that can be used to provide the property that is desired by the contractor as well as the owner and the specifier. Okay, thank you. So I believe at this point in time, Laura, I think we can take questions.
Thank you. We'll now begin the question and answer session. If you have a question, please press 0, then 1 on your touch-tone phone. If you wish to be removed from the queue, please press 0, then 2. If you're using a speakerphone, you may need to pick up the handset before pressing the numbers. Once again, if there are any questions, please press 0, then 1 on your touch-tone phone. Standing by for questions. Once again, for any questions, please press 0, then 1. And I'm showing no questions at this time.
Okay. All right. Well, thank you all for joining this webinar. And if you do come up with questions later on, feel free to contact me using the contact information that was provided to you. Thank you.
Thank you, ladies and gentlemen. This concludes this conference. Thank you for participating. You may now disconnect.